this is exciting. We're going to be able to work through a Calculus 3 multivariable calculus exam. And not just any one. The one from spring 2025 is exam 2. Yeah! And you know what that means? Differentiation. Yes, we're doing real calculus. This is going to be a lot of fun. Now there's 10 problems, 6 are multiple choice and 4 are workout. So we've got quite the journey ahead. As always, let's start by putting our name down legibly, because if we don't put our name, we're not going to get the credit. And we want the credit for all our wonderful ideas we're about to have. All right, let's get going. Number 1. Find f(x,y). Now, this notation, you see there's a tiny, very small subscripts here. This means we're taking two derivatives. One's with respect to x, one's with respect to y. We do them one at a time. So, we can say, well, what happens? Here's f. Let's take f sub x. So now we're going to take derivative with respect to x, treat y like a constant. So this y cubed, well, what is that going to be? It's going to be y cubed. Derivative of sine is cosine. So y cubed cosine x. And now, derivative of e to the x squared plus y. Well, it's e to the x squared plus y times the derivative of the inside chain rule. And the derivative of x squared plus y with respect to x is 2x. Now, they might have been sneaky and tried to put that in, but they didn't. So good, they're not very sneaky, because that's not the answer. That's round 1. We've got to go for 2 rounds, 2 derivatives. So, f(x,y) says, hey, take what you just did, but now take the derivative with respect to y. We're treating the x part like a constant. So, derivative of y cubed with respect to y, 3y squared. The cosine x is a constant. Say, well, we need a 3y squared cosine x, and that knocks out a bunch of options. Here, the x is a constant, and e to the x squared plus y, well, that'll be e to the x squared plus y times the derivative of x squared plus y, which is 1. So we need a 2x e to the x squared plus y. Well, that doesn't have it. And so, our answer is C. All right, straightforward. Integration. And we're going to do a lot of, not integration, differentiation. We're going to do a lot of that here. And so, let's get really comfortable, right? Know what you're differentiating with respect to, and remember, all the other things, treat them like constants. Okay, number 2. The vector valued function r of t is x of t, y of t, passes through the point p0, 2, 1, when t equals 5, with velocity vector v equals 3, 4. If f of xy is x sine pi y over 2, and g of t is f of x of t, y of t, find g prime of 5. All right. Whew. A lot to unpack here. And, okay, how can we start? Well, there's a few things. Let's remind ourselves, v. This really dates back to the previous exam. But what is v? Well, v is r prime. And we say, okay, so that says this is r prime. And what is that? Well, that's our x prime, y prime. So you say, oh, okay. So we have that x prime at a particular point, and not any point, just that particular point, t equals 5. So we have that r prime of 5, which is x prime of 5, y prime of 5, is equal to 3, 4. So there's our 3, and there's 4. How does that help us? Well, I don't know, but it's true, and I think it'll come into play in just a moment here. Because we want to make sure we understand what they gave us. It's very, very, very helpful to understand what's going on. All right, now, next. Well, what else do we have? Well, we have this g of t is f of x of t, y of t, and we're after g prime of 5. So notice that x and y are functions inside of f. So this looks like a chain rule. So I say, okay, great. Well, let's do that. So, and this is our most basic chain rule, right? It's f depends on x and y, which depends on t. I like to do this by drawing a chart. So this says g prime of t is, take the derivative of f with respect to x, so fx, x of t, y of t, times the derivative of x with respect to t. Well, that's derivative of x with respect to t, that's x prime of t. Add to that, running out of space here, so add the other part, derivative of f with respect to y, xt, y of t, times y prime of t. All right, now we're making progress here. We know a couple of things. What do we know? Well, we know what x prime of 5 and y prime of 5 are, right? And we're after g prime of 5. So g prime of 5, that's our f's of x of 5, y 5, x prime of 5, plus f sub y, x of 5, y of 5, y prime of 5. And we already went through great lengths to say we know what x prime and y prime are. Okay, so that says x prime of 5, this is 3, y prime of 5, this is 4. Now, what's next? Well, do we know what x and y are? Well, notice here, it passes through this point when t equals 5. Well, what that tells us here says, look, r of 5 is this point, 2, 1, because that's the point it passes through. Well, that's really x of 5, y of 5. So we say, okay, good. So we can now update these entries. So we're really after the following. We want fx at 2, 1 times 3 plus fy at 2, 1 times 4. So if we had those values, we'd be done. But how do we get them? We know f explicitly. So we're just going to compute them. All right, well, there's a lot of layers in this onion, but no tears. Only tears of joy that we get to say, look at this fun problem with all these pieces. And we can fit it together and make it work. All right, so f sub x, well, take derivative with respect to x, and that would be 1 times sine of pi y over 2. So at the point 2, 1, this becomes what? Well, we get fx at 2, 1 is, plug in x is 2, there's no x, y is 1, we get sine of pi halves. Well, sine of pi halves is 1. Okay, so this is 1. All right, now, on the other hand, if we compute f sub y, I guess we'll do it up here, what happens? F sub y is, x is now a constant, chain rule, so that's x times pi over 2 times cosine, because root of sine is cosine, pi y over 2. Now, at 2, 1, what happens? Well, we're going to get x is 2 times pi over 2 times cosine of pi over 2, which is 0. So we get 0. So this part is 0. So we have 1 times 3 plus 0 times 4, which is 3. I hope that's an option. It is! Yes! Oh my gosh. Wow. What a lot of work it feels like for a multiple choice problem. All right, but we got to pace ourselves. Got to save energy and enthusiasm because we still have 8 more problems left to go. 8 more opportunities for good times. Number 3. Given the function f of xyz is e to the power x plus y plus sine of yz, compute the directional derivative of f of xyz at 0, 1, 0 in the direction of the vector 2, 1, 2. Now, there's a big clue here where it tells us directional derivative. That's a clue that we want to do a directional derivative. Isn't it great when the problem is so explicitly telling you exactly what it's asking for? Okay, now, how do we do directional derivatives? Well, the answer is we take the gradient at our point dot the vector that represents the direction. Okay, so we have to tackle both of these pieces. Now, the direction, they gave us a vector. That vector, is it u? No. What's wrong with it? It's the right direction, right? It's the direction of that vector. But u is a unit vector. We need something that represents direction in a nice, pure way. And for that, we use unit vectors. So we're going to take the magnitude of 2, 1, negative 2. And if we compute that, that's the square root. 2 squared, 4. 1 squared, 1. Negative 2 squared is 4. Square root of 9, which is 3. So this vector has magnitude 3. So u is 1/3 to 1, negative 2. All right, good news. We have half of it. So we have a 1/3 to 1 minus 2. But we still have to do the other half. All right, so gradient of f. All right, well, let's begin that. For that, what's the gradient? Well, the gradient, it's going to show up again and again and again. So make sure you know how to compute it. It's the collection of partial derivatives. So the gradient of f looks like, generically, I'll write fx, fy, fz, just to remind ourselves, collection of partial derivatives. Okay, so derivative with respect to x, there's only one x. So that's e to the x plus y, comma, derivative with respect to y. Now, it's technically e to the x plus y times the derivative of x plus y, right? Don't forget the chain rule. I didn't forget it. I just didn't write it down. So there's a times 1 there. All right. Take now the derivative with respect to y. Same thing's going to happen. E to the x plus y times the derivative of x plus y with respect to y, which is 1. Derivative of sine, cosine. And then chain rule, derivative of the inside with respect to y is z. So plus z cosine yz, comma. Derivative with respect to z, it's only one term. So that's going to be a derivative of sine is cosine. Derivative of the inside with respect to z is y. So we get a y to come out, y cosine yz. All right, now though, we need to evaluate at the point because the directional derivative is a number. It's not a function. So gradient of f at 0, 1, 0. So x's become 0, y's become 1s, and z's become 0s. So we get what? E to the 1, e, comma, e to the 1, plus 0, right? Because it's 0 times something, comma. And now we have y, which is 1, times cosine 0. So that's 1. So e1. All right, so that goes here, e1. Don't forget dot product. Now we're almost done. We still have to remember how to do a dot product, though. So how does a dot product work? Well, we can just pull this constant out in front, 1/3 times, and you multiply entries together. 2 times e, 2e. E times 1, e. We're going to add that in. 1 times negative 2, negative 2. Right? So it's your multiplying entry by entry and adding up. Well, 2e plus e is 3e times a third makes e. 1/3 times minus 2 is minus 2/3. So we're looking for e minus 2/3. It's on the list. Of course it's on the list because we found the answer. No surprises. Some joy, but no surprises. All right, number 4. Which of the diagrams below gives the domain for the following function? So what do we have? Our function is f of xy is log of x minus y squared over 1 plus square root of 2 minus x. Now, I will say I recognize these pictures because I drew these pictures, but I did not have any hand in writing this test. They were just like, Steve, we like your pictures, so they recycled them. Okay. Now, when we're talking domain, we look for the problems. So there are 3 issues to be aware of. You should check for divide by 0. Don't want to do that. You should check for a square root of a negative, and you should check for a log of something less than or equal to 0. Essentially, these are your no-goes. You don't want that. No, 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 no. So make sure you're not doing any of those things. But as long as you're not doing any of those things, life is good. Life is wonderful. So we say, okay, where do we have issues? Do we have an issue with the divide by 0? No. Just because you have division doesn't mean you have a divide by 0 problem. Notice the square root of 2 minus x will always return something greater than or equal to 0. When you add 1, it's at least 1. Okay, so we don't have to worry about that. Now, could we have a square root of a negative? Yes, because we have a square root. So we say, well, that says because of the square root of 2 minus x, that tells us that we need the 2 minus x to not be negative. So it has to be greater than or equal to 0, or x has to be less than or equal to 2. So what does that tell us? Well, it says we cannot have anything which has x above 2. Notice here, E, that has some parts where x is above 2, and so does D. So we've now narrowed it down to one of those 3. Okay, our odds have improved. They're not 100%. 1 in 3, though, is better. Well, what else do we have? There's a log term. So the log of x minus y squared being there tells us something. It tells us that, you know what? We better have that x minus y squared is positive, strictly positive. Okay, so what is that? That says x has to be greater than y squared. So now we really have these 2 conditions. If you look at the 3 remaining pictures, they look the same. The only difference is in the dots and the solids, right? The dashes and the solids. Now remember, a dot, 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 this is a don't include, and that's when you have like a greater or a less than. A solid means do include. Okay, so notice what happens. This x less than or equal to 2, well, x equals 2 should be a solid line. That has a dashed line, that's out. Now, this x greater than y squared, that's a parabola turned on its side. So it's this piece here. But notice it's x strictly greater than y squared. So that curve should be a dashed line, not a solid line. So C is out. Meaning, the answer is B. And there we go. There you go. Yeah. Ha! What a lovely picture. A lovely picture. All right. Well, we're doing okay. We're doing fine. We're doing fine. No need to stress. Enjoy the experience. Let's go to our next problem. Number 5. Assume that an equation of the form f of xyz equals 0 defines y as a differentiable function of x and z. Use the following information to find partial y partial z. And it says, hey, f sub x is minus 2yz, f sub y, 3xz, f sub z is xy. Now you might be saying, ooh, what function does that? And the answer is, there is no function that does that. And you're like, what? Lies! We've been lied to! Well, but let's pretend like there were. Okay, all right, back on track. Given that this imaginary function has these partial derivatives, then what happens? Great question. So, there's a couple of ways to do this. One is you memorize formulas, and I'll talk about what the formulas are. And the other is you just say, oh, let's just remember how things work, which means we derive formulas. So I'll derive the formula, and then I'll say, but you could have also just done this. Okay, so here we go. Here we go. Notice there's a special thing here. Defines y as a differentiable function of x and z. What that means is that as we look at this, we say, oh, that says y really looks like y of x comma z. Okay? So that's what that means. All right, so what does that say? Well, it says we have f of x comma y of x comma z and comma z. All right, so here's the diagram that corresponds with this set of variables. We have our f at the top. It depends on x, y, and z, but y is a function of x and z. Now, we're going to take the derivative with respect to z. The way we know we're taking the derivative with respect to z is what's downstairs. So that tells us what you're taking the derivative with respect to. Because we see a partial y partial z, this really is saying, hey, this is partial z, the derivative with respect to z of y. All right, so take the derivative with respect to z. Where does z show up in the diagram? Shows up here and here. So, according to the diagram, if we take the derivative of both sides with respect to z, well, the derivative of the right-hand side is 0 is 0. So let's do the derivative of the left-hand side. Well, we have an f sub y, and then we say, well, y with z, right? F derivative with respect to y, y derivative with respect to z. What is the derivative of y with respect to z? It is what we're looking for, partial y partial z. Okay, now that's one path. The other path is f with respect to z. Or, rearranging it, you get partial y partial z is you subtract the f of z across, so you get a minus, and you divide by the f sub y. So that's the formula. So if you memorize the formula, then it's pretty straightforward. Now, here's the trick. There's a couple of things. One, there's a minus sign, don't forget that. And then you'll see how you have this y upstairs. It's going to match this y downstairs. And this, I've got to find enough colors. Here we go. I like this one. And this z downstairs has to match this z upstairs. So if you just sort of remember, hey, there's a minus, and then you sort of flip things around, then you can take any partial derivative of one thing with respect to another thing. It doesn't matter. Now, for us, to finish this up, that was the formula. That's how you derive it. But for us, we're almost done. We have to put the negative. What is fz? It is xy. What is fy? It is 3xz. And we're not out of the woods yet, but we're almost there. We just do some cleaning up. We can cancel an x, And we're left with a negative y over 3z. So we say, okay, is there anything that looks like negative y over 3z? Woohoo! Nice. Ah, wow. Cool. So if you're young and you have wonderful elastic minds that are full of memory banks, and you I have near infinite storage, go ahead and memorize this formula, and remember it works for f of x, y, z equals 0. Off you go. If not, just take the partial derivative and figure out how they all fit together. Both things work. Remember, on multiple choice, we're not testing you on how you get to the answer. We're testing you, did you get the answer? And so there you go, right? All right, number 6. By the way, if you're keeping track, our last multiple choice. Woo, how exciting, how exciting. Oh my gosh, it feels like we just started the multiple choice. All right, anyways, focus. We're given the function f of x, y is square root 9 minus x squared minus y squared. Find the direction of maximum increase for f at 2 minus 1. Now, there's a key phrase here. Direction of maximum increase. Yeah, it's not a word. It is a real phrase. There's lots of words involved in this going on. What is this testing? This is testing to say, hey, do you remember all the cool things that the gradient can do? So this is testing us on properties of the gradient. And it's good to know with properties of the gradient because they're like the derivative. And if we're doing a test about derivative stuff, it's going to show up. So the direction of maximum increase, that's going to be the direction of the gradient. The amount of maximum increase, by the way, is the magnitude of the gradient. So know your properties. So the gradient points in the direction of greatest increase. The size is the amount of greatest increase. Opposite of gradient, greatest decrease. Negative magnitude of gradient, amount of greatest decrease. Okay, so there's not a lot of things to test on in some sense. So expect everything to show up. So how is this going to unfold? Well, we're going to compute the gradient. And then we're basically done. The only thing that is left is they haven't explicitly said it, but I suspect looking at these expressions, they want a unit vector. Maybe not. Let's see. Well, let's figure it out. Because 3 of these vectors are unit vectors. And for some reason, 2 of them are not. And I don't know what they were thinking. I didn't write this problem, but we're going to do it. Okay, so I would start by saying let's make this problem a little bit more calculus friendly. So instead of the square root, we'll put 9 minus x squared minus y squared to the 1/2. And I say calculus friendly because it's easier to apply the rules when it's in this form. So our gradient of f, we take our partial derivatives. So, okay, chain rule. Taking derivative with respect to x. So 1/2 comes down. 9 minus x squared minus y squared to the minus 1/2. Right? The half comes down. Subtract 1 from the exponent. And don't forget, times by the derivative of the inside. Well, the derivative of 9 minus x squared minus y squared with respect to x, we're in the first slot, minus 2x, comma. All right, going to do the same thing. The 1/2 comes down. We get a 9 minus x squared minus y squared to the minus 1/2 times root of the inside, minus 2y. And we can do a few things really quickly. There's a halves and 2's. So we'll go ahead and cancel the halves and the 2's. And now, after we do that, we say, oh, look at this 9 minus x squared minus y squared to the minus 1/2. That's a common term. Let's pull that out. And we'll go ahead and rewrite that in our sort of non-calculus way, because we're not doing calculus right now. So we're just doing let's rewrite it. So that's our piece pulled out. And then we have minus x minus y. All right. Good. Now, what comes next? Well, we have to plug in the point. So gradient of f at 2 comma negative 1. Well, we'll get 1 over square root of 9 minus 4 minus 1. Right? 2 squared and negative 1 squared. Okay, we'll come back and play with this in a moment. And then we're going to get a minus 2 and a positive 1. All right, so what do we have? 9 minus 4 minus 1. Well, really, that's 9 minus 5, that's 4. And so we have 1 over square root of 4. That makes a half. So you have a half times negative 2, 1. All right. Nice! We did it! We found the gradient. And that's none of our options. Ah! Okay. All right, calm down, Steve. Calm down. We're almost there. Almost there. Now, well, so what's the direction of maximum increase? And so here you might say, well, we need something that's a scalar multiple of negative 2, 1. And that rules out 0, 1 and 0, 1 over root 5. This one looks kind of tempting, but you'll see the signs are wrong. Both of these are scalar multiples of negative 2, 1. One could maybe argue, but I'm not going to, that both of them have the right direction. But I think what they're mean to ask is to say the direction should be a unit vector. So one of these will be a unit vector, and we can just play around and figure out that the answer is D, but we can also practice. Say, well, take 1/2 magnitude of negative 2, 1, and the 1/2 comes out. So that comes out. We have negative 2 squared is 4, 1 squared is 1. So we get square root of 5 halves. Now divide. To divide is the same as multiply by the reciprocal. So we have 2 over root 5 times 1/2 times negative 2, 1. The 2's cancel. It gets us 1 over root 5 times negative 2, 1. And that's D. Now, as I said, we pretty much knew it was going to be either D or E. And then we're like, well, what's the difference? If you take the magnitudes really quickly, here's 4/5, here's 1/5. I'm squaring the entries when I say 4/5, 1/5. Add them together, you get 1. Unit. This is 4/3, 1/3. Add those together, you get 5/3. Not 1, not unit. So, all right. Well, I'll tell you, for multiple choice, that was a ride. But now we're into long answer. And for long answer, we've got to make sure we show our work, all of our work. Because if we skip steps, they may say, I don't trust you. So we have to be a little bit more careful. Now, let's begin. We have this function, log of x squared y plus 2xy. Part A, compute all first and second order derivatives of the function. Okay, when I see second order derivatives, I can almost tell without even looking at what comes next, there's only one or two things that might be showing up. It's second partials test or Taylor polynomial. It was Taylor. Okay, all right, no worries, no worries. Now, pro tip. Before you jump into anything, always ask yourself the question, should I simplify? In other words, can I rewrite this so that it's an easier thing to work with? Simplification should not be a 4-letter word because there's too many words in the word simplification to fit in 4 letters. So don't be afraid of doing simplification because it can save you a lot of heartache. And remember, we love ourselves. We want ourselves to succeed. So we say, okay, can we do anything? And the reason I ask is I see a log. So whenever I see a log, I say, can I pull it apart or maybe push it together? In this case, let's pull it apart. I can take this multiplication, becomes addition. And then the 2 can come down. So this is 2 log x plus log y plus 2xy. All right. I think that's going to make it a little bit easier for us to work with. Okay, so here we go. We have f sub x. So derivative 2 times derivative of log x, which is 1 over x. So that's 2 over x. Derivative of log y, 0. Derivative of 2xy, 2y. All right, f sub y. Okay, log x, that's 0. Derivative of log y, 1 over y. And derivative of 2xy with respect to y, 2x. All right, good. All right, now that's our first, but we also have to do second. All right, well, just give us a second here. So we can do fxx. It says look at f sub x. Take the derivative of that with respect to x. Well, derivative of 2 over x with respect to x. Think of it as 2 times x to the minus 1. The minus 1 comes down, so this becomes a minus 2. X to the minus 2, or minus 2 over x squared. Derivative of 2y with respect to x, 0. We can also do fxy. Right now, take the derivative of this with respect to y. Well, now the 2 over x is a constant. Derivative of 2y is 2. On a side note, if we wanted to, we could have also computed that one. This fxy is the same as fyx. We don't need to mark this down. But notice, again, check. Derivative of this f sub y with respect to x, 1 over y is a constant, and derivative of 2x is 2. You can just assume that. The cases where that's not true are super rare, and we never encounter them out in the wild. It's like you really have to work hard to make it so that's not true. And we don't work that hard, not on exams. So let's just assume these are always the same. And in some sense, that says, hey, you can use that to your advantage. When you're trying to compute the mixed partials, pick the one that's easier to work with. If they both look about the same, just flip a coin. fyy, so taking the derivative with respect to y. Derivative of 1 over y is minus 1 over y squared. And the derivative of 2x with respect to y is 0. Okay, and there we go. Now I just put these lines here just to emphasize where they were coming from. You don't actually need those. Those are our partial derivatives. And if I was being a little bit more careful, I might throw in some x and y's in there, but we're amongst friends, right? And so we all trust each other. We all know what we mean. Part B. Write the second order Taylor polynomial for the function around the point 1, 1. So second order means we're going to use up through the second order derivatives. That's why we did part A. And note the point. It's 1, 1. Now, let's write down the generic formula. So the generic formula for the second order Taylor polynomial around the point 1, 1. What does it look like? Well, it starts by saying plug in to the function. Whoops, not f. X, f at 1, 1. So this is just the 0th order. Plus fx at 1, 1 times, there's an x here, x minus 1. Y minus 1? Because x equals 1 at the point we're centered around. Plus fy 1, 1 times, and there's a y here, y minus 1. Now comes the fun part, the second order terms. Fxx at 1, 1 over 2. We'll explain the 2 in a second. See, there's an xx, so it becomes x minus 1 squared. So why the 2? if you were to take two derivatives with respect to x, right? Because we're trying to get two derivatives with respect to x, this 2 would come down, and then a 1 would come down. So I need something that will cancel out the 2 coming down. So that's why there's a 2 downstairs. Next, fxy at 1, 1 times, there's an xy, so an x minus 1, y minus 1, right? xy, and again, everything is minus 1s, right? Because we're starting at x equals 1, y equals 1. Why no 2 downstairs? Well, here, when I take it with respect to x, a 1 comes down. I take it with respect to y, a 1 comes down. I don't need to cancel anything. And I did not plan well, so add fyy at 1, 1. We're still going to have a 2 for the same reason, because of that y minus 1 squared. Now that's the generic formula. So what do we need? We need to actually find these numbers. So let's fill in the data. So let's start with f of 1, 1. f of 1, comma 1. So log of 1 is 0, log of 1 is 0, 2 times 1 is 2. Okay, so f11, 2. fx at 1, 1. Okay, so everything's a 1. 2 over 1 plus 2 is a 4. So we get plus 4 times x minus 1. fy at 1, 1. 1 plus 2, 3. So plus 3 times y minus 1, right? So we're just going through term by term. Now, let's go to the fxx. fxx at 1, 1 is negative 2. There's an over 2. So negative 2 over 2 makes a minus x minus 1 squared. All right, fxy at 1, 1. fxy at 1, 1 is positive 2. So this is a plus 2, x minus 1, y minus 1. And last part, fyy at 1, 1. Well, that's minus 1. That goes there. Minus 1/2 times y minus 1 squared. And there is the second order Taylor polynomial. Right? We have the generic expression, and then we plugged it in. Now you might say, hey, should we expand? No, don't expand. You definitely don't want to expand, especially when you see what's coming. The whole point of the Taylor polynomial is to say we are good approximations near our point of tangency, and to really take full advantage of that, you want to leave it in your x minus a's and your y minus b's. Okay, so we're ready for part C. All right, now, what do we have? Use part B, hello part B, to estimate f of 1.1 and 0.9. So this is our x, and here's our y that we're plugging in to this expression, because this is approximately f of x comma y near 1, 1. Now, let's take advantage of things. When we plug in x, we get x minus 1. Well, that's 1.1 minus 1, which is 0.1. On the other hand, when we plug in y, y minus 1 is going to become 0.9 minus 1, and that's negative 0.1. So, we get 2 plus 4 times 0.1. All right? And then plus 3 times negative 0.1. Okay? Minus 0.1 quantity squared plus 2 times 0.1 times negative 0.1. All right? And then minus 1/2 times negative 0.1 squared. Now, At this point, we hope, I hope we don't have to simplify. But then I noticed it says, simplify your answer to a single number. I'm so sorry. What have we done to offend you, calculus teachers? No. Come on, we love our teachers because they loved us first. So we're going to do this. We're going to be really careful and go through. So what do we have? We have 2 plus 0.4 minus 0.3. And 0.1 squared is 0.01. So minus 0.01. Now, here, there's a minus. Now, 0.1 times 0.1 is 0.01 times 2, so 0.02. And then we have this part. Now, the minus being squared is the same as positive being squared, so it's still a minus. And I'm going to be really careful here. So this 1/2 is the same as 0.5. Then we have a times a 0.1 times a 0.1. Well, 5 times 1 times 1 is 5, but we need to move the decimal place 3 times. So this is subtract a 0.005. Okay, 0.4 minus 0.3 is 0.1. Okay, then we have 0.01 minus 0.02 minus 0.005. We can just do those together. So that's minus 0.035. All right, so we have 2 plus 0.1 subtract 0.035. Well, okay. If you take 0.1 subtract 0.035, what will you get? You'll get a number, right? Yeah. Okay. Which number, Steve? Come on. What's the number? All right. It's going to be 2.965. All right. Now you can check. If you add 0.035, then you get 2.97, and then you get to add the 3. That becomes, whoops, I messed that up. That is not right. Okay, all right. Boy, I feel like I'm having to go back to the days when I was doing math. Yeah, those were good days. I miss those days. It's 2.065. There we go. If you add 0.035 to 0.065, you get 0.1, which is that. 2.1, which is good. There we go. Oh. Well, the good news is that was probably just worth a single point. So if you were stressing out about it and you're like, I'm going to lose so many points, notice something here. I want to point this out. Where did most of the points come from? Half the points came at the very beginning. And this should be the low-hanging fruit. A lot of problems are set up this way. So a lot of problems, they look like they're going to be super stressful. Like, how can we make any progress? But even if you can make just a little bit of progress at the very start, you'll get 3, 4, 5 out of 10. Don't underestimate the value of a good start. And that'll get you pretty far along in the process. All right. Well, Interesting. Well, we got to keep going, right? We only have so much time. We've still got 3 problems to go. Number 8. Find the unique point at which the function f of xy equals 4x squared minus 8x plus y squared plus 2y attains its absolute minimum value on the set defined by the equality x squared plus y squared over 4 equals 1. Okay, so we have a constraint. And if you're familiar with this constraint, this is actually not a very bad shape. In fact, it's an ellipse. And it's an ellipse that goes 1 in the y direction, and then it actually goes up 1 in the x and 2 in the y. So this is the curve. And we want to be on the curve. So notice, it's not a curve and then the interior. That's a different type of problem. It's the curve itself. So when you see a problem where you have a constraint, you say, I know what this is. This is Lagrange. Lagrange. Do you think there's any relationship to l'hôpital? Lagrange, mon ami. Maybe. They could have been friends. Well, no, they couldn't have been friends. but it's fun to imagine that if they had lived as contemporaries, then they could have been friends. All right, so Lagrange multipliers. All right, now, how does this work? Well, we have a constraint. So, yay us. So now we say, well, what's another constraint? And for that, we say, Lagrange multiplier says, look for where gradient of f equals lambda gradient of g, which says that we really have a pair of equations. F sub x equals lambda g sub x, and f sub y equals lambda g sub y. Well, okay, what does this become? Take the derivatives. Derivative of f with respect to x is 8x minus 8 equals lambda. Derivative of g, now you might say, well, where is g? G is the constraint curve. So this is your g. G with respect to x is 2x. All right, and now we say, okay, what about f sub y? Well, derivative of f with respect to y, that would be nothing, and then we get 2y plus 2. And that equals lambda derivative of g with respect to y. And that would be, that goes away, and so that's 1/2, right? 2/4 is 1/2 times y. All right, and good. Now, how do we proceed? So here's the thing. What we're going to do is we're going to take our problem as given, and we're going to say we're going to turn it into 2 equations and 2 unknowns. One of our equations is our constraint. So we're going to have the equation x squared plus, I'll write it as 1/4 y squared equals 1. That's equation number 1. Equation number 2 is going to come from working through this relationship. My advice is solve for lambda. It works really well. So, what does that mean? Well, what is lambda? From the first equation, you say it's 8x minus 8 over 2x. But you'd also say, from the second equation, it's 2y plus 2 over 1/2 y. Now, I will say there's a technicality. What if lambda were 0? Okay, yes, there's that technicality, but please don't stress about that. We're not going to ask you those kinds of technicalities. Do the process. Trust the process. All right, now from here, cross multiply, and we're going to get some equations. So we get 1/2 times y times 8x minus 8, and that's going to equal 2x times 2y plus 2. You might say, hey, those look like the pieces all sort of jumbled together. They are, and however you get to this, that's great. But the point is, get to it. If we multiply through, 1/2 times y times 8x is 4xy, 1/2 y minus 8y minus 4y. Here, 2x times 2y, 4xy, and 2x times 2 is 4x. The 4xy's cancel, That's good news. The 4's cancel. That's good news. And we get this equation, x equals minus y. So that is our second equation. So now we're like, cool, 2 equations and 2 unknowns. And we solve. And we say, okay, well, not too bad. Not too bad at all, actually, because that second equation can quickly get us down to 1 equation, 1 unknown. Put it in x equals minus y. Minus y squared will give us what? So I'm just going to make a note. 2 equations, 2 unknowns. I want to write that down. Not that they're going to give me any credit for writing that down, but just to remind myself of the process. All right, putting in x equals minus y, we get y squared plus 1/4 y squared equals 1. Or 5/4 y squared equals 1. Or y squared equals 4/5. Or y is the square root of 4/5, which is 2 over square root of 5. But be extra careful. You'll often, in solving problems like this, run into a y squared. What do you need to not forget? Don't forget the plus minus. That's right. Don't forget it. Be smart. Remember it. Because if you forget it, you'll say, oh, I only have 1 point. It must be the answer. No. That's not how it works. You should expect 2 points, right? Because if you step back for a second, this region is closed and bounded. So it has an absolute max and an absolute min. And so we definitely have to come up with at least 2 points because there has to be an absolute max and an absolute min. Now the good news is we only need the absolute min. And so we're close. Now we're not there yet. So remember, x is negative y. So we're going to get 2 points. So if we have, let me blockade off some pieces here, positive 2 over root 5, then x is negative that, so that's minus 2 over root 5. And if we're at minus 2 over root 5, then x will be the positive that, so that's 2 over root 5. All right, so we've made a list. And notice we are after the point. One of these will attain a larger value than the other. In fact, one of these is going to be the absolute max. One of them will be the absolute min. How do we find out? Well, quiet, pens. The way we find out is we plug it back into f. Okay. All right. So here we go. I'm going to write down for reference f of xy, 4x squared minus 8x plus y squared plus 2y. All right. We've got to plug both points in. So f of minus 2 over root 5, comma 2 over root 5. And when you square and either one of these, you get 4/5. So you get 4 times 4/5, and minus 8 times minus 2/5 is plus 16, right? Minus 8, I said 2/5, 2 over root 5. Minus 8, so that's 16 over root 5. Y squared, that's again a 4/5. Then plus 2 times 2 over root 5, that's a 4 over root 5. And so if you put that together, we get 16 over 5 plus 4 over 5, that's 20 over 5, which is 4 plus 20 over root 5. If we plug in at the other point, 2 over root 5 minus 2 over root 5, well, okay, when you square, still get a 4/5. Minus 8 times 2 over root 5 is minus 16 over root 5. Minus 2 over root 5 squared is, again, 4/5. And then we're going to have 2 times minus 2 over root 5. That's minus 4 over root 5. And so 16 fifths plus 4 fifths is 20 fifths, which is 4. Minus 16 over root 5 minus 4 over root 5 is minus 20 over root 5. And now, which one's a smaller value? Well, the 4 minus is going to be smaller than the 4 plus. So this here, this is the smaller value. So this must be our absolute min. It's smaller. This is our absolute max. It's bigger. Finally, let's make sure we know what we're looking for. Where's the unique single point at which this function hits the absolute min on the set? Our answer is a point. It's not asking us for the value, it's asking us for the point. So we would finally say we attain the absolute min at, and that's this point, 2 over root 5, comma, negative 2 over root 5. And there's the answer. Whew, nice, nice. All right, let's keep going. Number 9, find and classify the critical points. Classic problem. They love these problems. Mwah. They just, okay, if there's not a lot of things that I can say for sure give me on the test. Actually, I can pretty much predict what most of the tests will look like because they all are very similar. But this is one of those things that you're just like, I can feel it coming. I can sense it coming. And say, okay, so there's 2 stages. There's the find stage, and that's where you set the gradient equal to 0. The classify, this is where you use the second partials test. It's like the second derivative test, but for multivariable functions. And, okay, so let's start. Gradient of f equals 0. We really are saying that 0 is equal to f sub x is equal to, and now take the derivative with respect to x, 5x to the 4th minus 5y. And 0 is equal to f sub y is equal to derivative with respect to y, minus 5x plus y to the 5th. And, whoops, not y to the 5th, 5y to the 4th. I know it's been a long test, but we got to stay focused. Keep your energy up. You know, you can do this. You can definitely do this. All right. 2 equations, 2 unknowns. So, from the first equation, what can we say? Well, you can divide out by the 5, and this leads us to the equation y equals x to the 4th. And in the second equation, again, you can divide out by 5. You get x equals y to the 4th. Like, wow, okay. What satisfies those equations? Well, you get y is equal to y to the 4th, which is y. 4 times 4 is 16. And now from here, you can use a little bit of rearranging. 0 equals y to the 16 minus y, or that's y times y to the 15th minus 1. Well, that gives us 2 possibilities. Y equals 0, or y to the 15th equals 1. Well, there's only one number that's real, and when you raise it to the 15th power, it gives you 1, and that's y equals 1. And so we say, aha, that leads us to 2 solutions. So if y equals 0, x equals y to the 4th, so that leads us to 0, 0. If y equals 1, x is 1 to the 4th, that leads us to 1, 1. All right, so that's the find stage. So we have 2 critical points. So we have a critical point of 0, 0, and a critical point of 1, 1. So here's a critical point. All right, good. Now, classify. For the classifying, you got to do the second partials test. Now, the good news is it's basically hard-coded into the formula sheet. There's this value called d, I'll talk about in a second, if that value is negative, you have a saddle. If the value is positive, you split and say, well, if fxx is positive, it's a min. And you can say local min, but we're not going to go into that fine of details. If fxx is negative, it's a max. What is this value of d? D is computed by fxx at AB fyy, AB minus fxy at AB quantity squared. So we call it second partials because you need to look at the second derivative of all the possible second derivatives together. It's also second partials because it really is the analog of the second derivative test for multivariable functions. How do the second derivatives drive the behavior given that the first derivatives are 0? So we're going to have to key off of this. So it's good to be organized with your partial derivatives. So fxx, take the derivative with respect to x, that's 20x cubed. fxy will be negative 5. It's the same as fyx. And fyy, well, that's going to be 20 y cubed. So we get that d, generically, that's 20x cubed times 20y cubed minus negative 5 squared. And negative 5 squared means we're subtracting 25. All right, so at 0, 0, we get that d is 0 times 0 minus 25. Well, we don't care about the value, we care about the sign. It's negative. Saddle. It's not surprising to encounter saddles. Saddles are fairly frequent. So don't stress if you see a saddle. So 0, 0 is a saddle. All right, well, great. That's something. But we're not done yet. So what happens at 1, 1? Well, we get 20 times 20 minus 25. That's 400. Subtract 25. We don't need to know that that's 375. We just need to say, hey, that's positive. And notice that both of these terms, fxx, fyy, are positive. So d is positive. The second derivative with respect to x is positive. That says we're at a min. So 1, 1, that is a min. Now you can be a little bit more specific and say local min, but min, that's good enough for me. And there's the process. So again, find and classify. Classic problem. You see this all the time. Take your partial derivative, set it equal to 0, solve. You got your classic 2 equations, 2 unknowns, and all right, then go to your second partials test, follow the formula sheet, and you'll get your classification. Oh, our last problem, which is good because we're almost out of time. Number 10, find parametric equations for the normal line to the surface x squared minus 8xyz plus y squared plus 6z squared equals 0 at the point 1, 1, 1. And so if you plug in 1, 1, 1, you'll get 1 minus 8 plus 1 plus 6, which is 0. So 1, 1, 1 is on the surface. What's our intuition here? Well, what's going on is there's some surface out there. It's hard for us to imagine exactly what the surface is doing, but here's this surface, and on this surface, there's this point. And what we want is we want a line which is normal to this surface. What does normal mean? Normal, whenever you see normal, you should think of perpendicular. So somehow it's perpendicular to the surface. And you say, okay, well, that's good. Now there's one other useful piece, which is to say, hey, how do you make a line? Well, a line has 2 main pieces. You have x naught, y naught, z naught, and you have an a t, b times t, and c times t. Where, let's be careful here, x naught, y naught, z naught, that is the point on the line. Now I say the point, but any point will do. We just need one. And on the other hand, the a, b, c, that is the direction vector. Okay, good. So, all right, direction vector. So, we have to find those two pieces. The points given to us. Nice! Woohoo! Halfway done. Halfway done. Which means we still have half to go. Now, the direction vector. We need something perpendicular to the surface. So we start thinking, what's perpendicular to things? And that's when we have the great aha. If we have something that looks like g of x, y, z equals a constant, in our case the constant is 0, then the gradient of g at P is perpendicular to the surface at P. So the gradient is perpendicular. That's the direction vector. All right, now, key thing, you have to have this equals 0, but we already do. So we say perfect. So here's our function. We take our gradient. So the gradient of g, take derivative with respect to x, 2x minus 8yz. And that's it. Derivative with respect to y. Minus 8xz plus 2y, comma. Derivative with respect to z. Minus 8xy plus 12z. Now, that's the gradient at any point. We need to evaluate it at our specific point. So the gradient of g at 1, 1, 1, plug in 1. Plug in 1 is great. 0 and 1 are our two favorite numbers to plug in. Because to plug in 0, lots of things drop out. To plug in 1, usually you look at coefficients. So we get 2 minus 8, negative 6. Negative 8 plus 2, negative 6. Okay, well, that's fine. Negative 8 plus 12, 4. You don't have to normalize this. You don't have to make it a unit vector. That goes to your direction vector. So we now have all our pieces. So we write it down. X equals, y equals, z equals. Our point is 1, 1, 1. 1, 1, 1. Then we have our A, B, C. Right, A, B, C. So minus 6t, minus 6t, plus 4t. Are there other ways we could write the line? Absolutely. But we only need to have a version that works. So that's why I say as soon as you have it, you're good. There's nothing that says that their direction vector has to be a unit vector. It just has to point somewhere in the direction along the line. And check out the time. We made it. Woohoo! Drop the pen. Yes! And we have enough time to walk up to the front and be like, booyah, we did it. We got this test done. All right, now, I know we're on an adrenaline high. Let's pull it back down for just a second. Thank you. Thanks for doing the test with me. This one, there's some challenges here. But if we're patient and methodical, we can do it. You will have a different test, so I don't want you to be panicking about this test. There's no sense to panic about the test that came before. Focus on the challenge that lies before you. The set of problems that are on here are actually pretty good. The topics are a good representation of what you might see. So there's lots of good that comes from the practice. So put in the time, make sure you understand the concepts, and be ready. Because you never know that there might be a professor out there that's going to throw a curveball. But sometimes the ones that look the most challenging turn out to be the most beautiful. All right. Well, again, thanks for joining me. Good luck, and I hope to see you again. Bye.